Okay, yeah, one day to volleyball. Now there's a MATLAB class from 4 to 6, and then the graphics class from 6 to 8:30. Y'all are both, you probably all are in those. Are any of you in the graphics class? Okay, good. Just MATLAB. Okay. Which is online. You never go. Good. Yeah. So yeah, I'm looking forward to it. I actually I had agreed to sub for the graphics class, like crap, but I think I can find something. Anyway, yeah, I kind of messed up the lecture on Monday, so I have fixed it, and I'm not gonna re-download it, but here's the fixed one, and I know I didn't even give these out to you, so this you can pick this up later, I think, because I don't know, we don't want to wait for you to write all this stuff. This is kind of really dull stuff. And this was my example here, and then it was this slide here that I didn't quite finish, but you're right, Mason's right. It looks exactly the same as the formula for the inductor. So it's just minus W's minus omega C Vm squared 1/2 sine 2 omega T. I was kind of messed up because what happened was in this one, we started with a current of I cosine omega T, but then on the capacitor it was a voltage, which is V cosine omega T. And what I had remembered is how the power is sort of flipped. The average power. Wait, I'm not even looking at the right slides. So this is the stuff in the slide, and I said fix this because I didn't finish this. So it is minus omega C Vm squared. But they're switching which one's the reference, right? Here the current is the reference, here the voltage is the reference. I had remembered there was a sign flip for one versus the other. And it is if you look at them with the same reference. So in the next slide, I actually did this is the in general one. This is another one where I kind of think I ran out of time here. Well, there was this thing too that I had to switch on mine, but or did we do this one? Did we get this one through already? So the point is, in general, with some passive linear network of inductors, capacitors, resistors, you're going to get an equivalent impedance, which you actually measured yesterday in the lab, which is kind of cool. You kind of get how that works, which you can kind of express in polar form, z angle theta, or r plus jx. And if you know the current is a phasor and the voltage is a phasor, the voltage is like a Vm angle 0, and the current is a Im angle minus theta. Then you can find current using Ohm's law in complex form, so V over Z, and that is the magnitude of the voltage over the magnitude of the impedance and the difference of the angles, right? So this is the value of Im here. So it's Im angle minus theta. Did we do all this? I can't remember how much we did. I guess I can pull it up here. This is what we had been doing. We got most of this thing. That's power AC circuits. There's this, and then there was this. Yeah, there's some extra stuff that I didn't cover, which you can kind of sketch in if you want to. So the power, the instantaneous power is always, what's really happening is the instantaneous power, moment to moment. It's fluctuating. Sometimes it's higher, sometimes it's lower, sometimes energy is being absorbed, sometimes energy is being released into the circuit. And this is the guiding function, the guiding formula for that, which we can kind of simplify and have these two terms, which we pull out of this thing. The one term doesn't have any time component. It's the average power, which is Vm over 2 cosine of theta. That's taken from this area here. And another interesting term which we pull out is the reactive power, which is coming in on the sine component, and it is sine omega t component. It is Vm sine of theta over 2. And we call this the reactive power, which is indicative of the energy that's kind of temporarily being stored by the capacitor or inductor and then released back into the circuit. So it's kind of an ebb and flow thing, and it's sort of an indication of how sort of an indication, I guess, it's an indication kind of how tall the power sine wave is, right? If it's really tall, then that means you're getting a lot of amplitude there on the reactive side. Maybe. These are actually kind of mysterious things, but oops, I went and, and then we did we do the power triangle? Did we get that far? No, maybe not. Yeah, so we got as far as here, right? And then the next part is we can express this in terms of another triangle, which is the power triangle. So really, you know, we're looking at this really messy thing here, which has all these terms in it. And we're pulling out the capital P term, which is this is called the average power, right? We got that circled there, this underlined here. This is the average power, and this is the actual stuff that we can actually get work out of, whether it's heating up a room or moving clothes around in your dryer. That's what the average power is being used for. The reactive power isn't doing anything for us. It's just temporarily being stored and released into the circuit, but we do need to track that. So what we do is we another term, another thing that kind of shows up a lot is this Vm over 2. You can kind of see that happening, and we can define a new term S, which is Vm over 2, which is Vm over root 2 times Im over root 2, but Vm over root 2 and Im over root 2 is the RMS or the effective values of the voltage and current, right? And so this is another term, S is the apparent power in the unit of VAs. And a watt is a volt times an amp, so it's another way of talking about watts, really. But it's the same. It's just kind of given in VA, so you know we're talking about apparent powers as opposed to average power. Mason? Yeah, RMS. You could also have written RMS. Effective and RMS mean the same thing. And this is a convenient term because when you look back at the formula, you can see that this average power is this thing here. This is S cosine of theta, and for Q it's S sine of theta, right? And that leads you to a triangle kind of formulation, right? Because if P equals S cosine of theta, and the units of P are, of course, watts, and Q equals S sine theta, and the units of Q are in vars, which stands for, anybody remember? You got in your notes? Volt, amp, reactive. So it's talking about reactive power, stuff that we're not really even able to make use of. And we can form a power triangle with these notions. And in this case, the S is the Vm by m over 2, which is V effective by effective. That's the hypotenuse of the triangle. And then P, which is the average or real power, is going to be S cosine of theta. This angle here is theta. And Q is S sine of theta. Oops, S sine of theta, not sine of theta. Mason?
What does it say after the comma, after equals S sine theta?
VARS.
Vars?
Yeah, VARS. That's the unit of reactive power. It stands for volt amp reactive. What's theta? Where did theta come from? Phase difference between the volt and the current, right? Yeah. Good. Yeah, it's the phase. This is the theta right here. It's the phase angle difference between the voltage and the current. And that essentially is determining the angle of that triangle. We call theta also the power factor angle. And the cosine of theta is called the power factor. That theta is, it appears as the phase of the current, but that theta also happens to be the theta of Z equivalent, which you measured in the lab. Remember how you could convert that? That was the weird thing, right? When you measured the phase angle of the current relative to the voltage, it turned out to be the same as the angle of the impedance that you calculated, right? It was the same angle. And that's the connection between those two, right? So the impedance triangle has the same angle in it because that also relates the voltage and the current. So the impedance triangle is when we define Z as R plus some J times some X reactive component, that you can write this, try to draw it so it has the same slope. R X theta and then Z. So basically the ratio between the resistive and the reactive impedance, between R and X is the same ratio as that between the average power and the reactive power that circuit will process or whatever. So they're very closely related. And therefore, also, it kind of makes sense to think of, impedance as a complex number. Maybe we can think of power as a complex number as well. These complex numbers are just these convenient tools to represent stuff that has a magnitude and an angle, or two components that you want to kind of manage properly, right? So let's talk about complex power then as S bar. So S without the bar is apparent power. S with a bar is a complex number. It's complex power P plus JQ. Now we're a little far from where we started with the instantaneous power, but it's just it's a convenience, right? This is why we're using these things. And what that equals, if if you have a voltage and a current, it's the magnitude of the voltage, magnitude of the current over 2, angle, phase difference between them. And the magnitude of S bar is going to be S, which is the hypotenuse of that power triangle, right? That's the apparent power, right? And that's, Vm Im over 2, as we saw. And of course, P equals S cosine. We're just repeating all this stuff. Q equals S sine of theta. And if we define, V bar, the phasor of our voltage, as some Vm angle theta V, arbitrary phase angle, and our current as some Im angle theta I, and we have some impedance that they're going, so these are all related to an impedance that they're driving, or related to going, the voltage of across the impedance and the current going through that impedance is related by V equals Z bar I bar, and I bar equals V bar over Z bar. And that means that's Vm over Z with an angle of theta V over an angle of theta, just plain old theta for the impedance. And that equals then Im angle of theta V minus theta. This is there's a lot of gibberish here. It's we're kind of exploring the relationships between all these guys and coming to terms with it. But what's interesting is if you talk about the complex conjugate of I, that's another interesting term here. So I star. What's the complex conjugate? What is that? Remember what that is? Been a while since the last time you saw it was probably algebra 2, right? Or have they brought in complex numbers more often? Nobody remembers what the complex conjugate is? Mark? Yeah, you flip the sign of the imaginary part, right? So if I is this, another way to flip the sign of the imaginary part is to just negate the angle, right? Because if you have an angle of theta from the x-axis, the angle of minus theta from the x-axis is going to go in the opposite direction. So you're going to have an opposite, a negative imaginary part, but the real part will be the same. So so this I star is Im angle of minus theta I, which is Im angle of theta minus theta V. And this S bar can actually be written then as, see if this actually makes sense. S bar can be written as, it actually it's one of these weird conveniences. Like if you know the V and the I, it can be written as 1/2 V bar I star. I bar star, complex conjugate of I. And that's because we've got this one half of Vm angle theta V times Im angle of theta minus theta V, right? Because that's what I star is. It turns out if we take the complex conjugate, we get this convenient thing where what happens is, you know, we're multiplying two numbers in polar form. The magnitudes multiply, but the angles add up, right? So you have to add theta V plus theta minus theta V. And this is going to turn out to be 1/2 Vm angle of theta V plus theta minus theta V, right? Those cancel. So that's 1/2 Vm angle theta. The angle theta being the difference between the voltage and the current phases. And so the formula is, it's a pretty nifty formula. Again, it's just one of those things, we're just sort of hacking complex numbers to be able to do this a little more conveniently. That is the formula for complex power, and which also equals P plus JQ as a result of. And a little more, if you're not getting the whole complex conjugate, what I was kind of saying is the complex conjugate. This is the conjugate of I. And that's where, you know, if you have an I that's defined with some theta I as an imaginary part, the complex conjugate is going to be that same magnitude, but with a negative angle. Well, this is all just baseline to doing some interesting calculations with power and getting a handle on it. You know, I never got this stuff when I was in college. We went in a different direction, but it's really useful stuff. And especially, I think a large portion of you all are going to be mechanical engineers. Is that right? Oh, Daniel, your computer. Everybody else is either physics. Well, Hong is sort of undecided too. But everybody else is. Good. Oh, good. Double E. Yeah. Yeah. You don't know Elmer, do you? He was up at Santa Cruz. He was originally going to be computer engineering and decided to just go straight double E. I think he liked the math. Probably usually if you like the math more, I think it's a really cool field. Double E is very math heavy. And that's why you're going to double major in math and double E, right? Just double E? Okay, cool. Yeah, so anyway, so now we can do some power calculations. And in a circuit like this, and this is actually a very industrial thing, like if you studied to be an electrician, like if you just wanted to, you know, wire factories, you know, with power, so if you have to understand all this stuff, it's the kind of thing. My brother's an electrician, and he kind of got all that stuff. And I think they often teach it to electricians without the whole complex number thing, I think. And you can do it without complex numbers, just with the basic straight trig, right? So it's a little less confusing. But complex numbers makes it easy. So we're asked to find in this circuit, the power factor, which, as a reminder, is the cosine of the of the theta of the impedance, right? If you know the angle of the impedance, it's the cosine of that. And then the real, which is the average, and reactive and apparent power. So that's P, Q, and S. And another thing you'll sometimes see is the voltage of the signal phasor is in RMS. That means we're going to use the formula without dividing by 2 in it, right? So you have to remember that. If you get to that point where you're calculating the complex power, you would just use the RMS values without dividing by 2, because they've already got that in there. So for A, we find the, we can start with just the equivalent impedance of that circuit. So Z equivalent is going to be 6 plus the parallel combination of 4 and minus J2. So 4 times minus J2 over 4 minus J2. And that is going to be 7 altogether, I guess, 7 angle minus 13.24 ohms. So this is the angle theta. It represents the phase difference between the voltage and the current phases. And the power factor is going to equal cosine of minus 13.24, that angle theta, which is 0.9734. And we call this a leading power factor. And that relates to the measurements you did yesterday in the lab, right? So those measurements where you measured the phase of the current and the phase, remember Eli the Iceman, right? The first circuit we looked at was a capacitive circuit, and you found it had a negative angle, right? But then when you measured the, and that was the thing where, you had the current, let me do this in color. The current maybe was in blue, and this is your I, and the voltage was maybe in green, and the current was sort of peaking a little before the voltage, right? And you measured this angle here. You found that angle experimentally in degrees, right? And that was considered a positive angle, but it turned out when you did the impedance, because it's V over I, you got a negative impedance angle, right? And that's the consistent for a capacitive load. And that's where the current leads, oops, say leads. Voltage. That's why it's a leading power factor. So when someone says it's a leading power factor, then that tells you it's a capacitive load. If it's a lagging power factor, it's the opposite. It's an inductive load. And this angle kind of relates to, our Z too. So that's the same angle. So that angle theta is relating to our Z equivalent, which can be some, this magnitude angle theta. And R and JX. And this is the same angle theta. And this is ICE. current leads voltage, potential in the capacitor. So anyway, that's some setting some light on that. So then, well, then how are we going to find the real and average, the real and reactive and apparent power? We can find the effective RMS current, which is going to be our source voltage divided by our equivalent impedance of that whole circuit. So this is the I that we are defining here going in, the phasor as well. So that's going to be 30 angle 0 over 7 angle minus 13.24. And that equals 4.286 angle of 13.24. That's why you get a positive phase angle for current when it leads the voltage. So that's your effective RMS current, and then the complex power is going to be 1/2 V I star, or the effective I effective star. So we have to take the complex conjugate of the current to make this work out right. So that's going to be 30 angle 0 times 4.286, but now we flip the sign again. And we get 128.58 angle of minus 13.24. So the S, right, is a complex number, so that's our S bar, and that equals 128.58 cosine of minus 13.24 plus J times 28.58 sine of minus 13.24. And that gives us 125.16 minus J 29.25. And so I kind of ran out of room here. Do I have room on the next slide? Probably do it on the left here. So that means that P equals 125 watts. The reactive Q is this is the real power. Reactive minus 29.25. And the apparent, I'm really running out of room here, apparent. This is the magnitude, it's just going to be 128.58 VAs. You can squeeze that all in there. That is the answer.
So the current is that whole thing as far as
Pardon me?
When you ask for the apparent power, that is the whole complex S bar.
No, the complex power is S bar. The apparent power is the magnitude of S bar.
Oh,
Yeah. Okay, so that's that. And another interesting thing we can do is maximum average power transfer. We talked about this, yeah, Mason?
If we want yes, in terms of RMS,
Yeah.
that would be the measure, right? So,
Well, it's just a divide by 2. If you're not giving it an RMS, if you're given the voltage as a magnitude, then you'll find the current as a magnitude, and then just the S is going to be 1/2 of V times I. Hi. They probably meant 201, I think. Yeah, there's a, if you go through the glass doors, the first door on the left, yeah, check in there, yeah. Yeah, so it's just dividing by 2 if you get it in magnitudes. No, if you get it in magnitudes, it's 1/2 of the product of the magnitudes of the voltage. Yeah, because each one of them is divided by square root of 2, so that squares that and gives you a 2. But the question can come back now to, in terms of power, and this is actually maybe more important than the one we looked at with DC power, the average power transfer for AC circuits. A lot of times, you know, if you're running in a power system mode, you're designing a factory or, you know, putting power where it's going to be consumed, you want to get the maximum power often to the load. And yet you've got some maybe, you know, impedance in your transmission setup. The power companies, you know, they have to send us their power over very long wires, right? And there's some impedance in those wires. And but the question is, given that, what's the maximum power we can get to a load, given the whole system, right? A source, some transmission line or something, and a load. And then, you know, what load should we use to get the most power to the load? And so what value of ZL will give us the maximum average power, and then kind of finding out what that is. Again, this is a lot of, not too bad, it's a fair amount of chicken scratch kind of stuff, but one thing we can kind of see off the bat is the, I here is going to be basically is going to be defined as the, if you know the Thevenin voltage, V Thevenin, we know how to do that already, V Thevenin over Z Thevenin plus ZL. And, you know, that gives us the Z Thevenin, of course, has a real and imaginary part, so does the load. So that's, you know, this whole thing is going to be an R Thevenin plus JX Thevenin plus RL plus JXL. We got to look at those 4 different components. And we can use a little shorthand. The power to the load is going to be I squared effective times RL which would, if you didn't have it in effective form, if you just had it in magnitude, it would be 1/2 I bar squared for L. So we can take I Thevenin and find out that that is well V Thevenin over Z Thevenin plus ZL, right? And we square that, and we're going to get V Thevenin squared over those guys. So this is sort of setting us up for the square of that. So we can rewrite the power of the load as in terms of our V Thevenin. It's a little more convenient that way. And so we're squaring basically I bar, V Thevenin squared over Z Thevenin, which is going to be R Thevenin plus, so we group the real and imaginary parts here. We group these guys, we group these guys, so it's going to be R Thevenin plus RL squared plus X Thevenin plus XL squared. And I think we're actually looking at magnitudes, not so we're talking about, if we want to talk about, the magnitude of I is going to give us the magnitude of the power. It's going to be the magnitude of V Thevenin over the square root of R Thevenin. This is a little bit of a hand-wavy thing, but it's showing you kind of the reasoning behind how we're going to do this calculation, X Thevenin plus X L squared. Because when you square that, you get this thing. And this is going to be the magnitude of the power. And of course, if we're doing it with magnitudes, not RMS, we have to divide this by 2 to take care of that. So we'll leave the 2 in there just to assume that we're using magnitudes, not RMS values. It's just, I don't know, it tends to be, maybe we can put a 1/2 there so you don't get that. And the, let's see. One way we can maximize the load is to set the imaginary part of that sum equal to 0, right? So in other words, if we set X Thevenin plus XL equal to 0, then that would imply that we would want to choose the reactance of the load to be the opposite of the reactance of the Thevenin circuit. Okay, that would allow us to just cross out that term right there, giving us more power, right? And simplifying our analysis considerably. Because in the same way we did it for DC circuits, then we're just left with power as a function of RL, which is going to be V Thevenin squared. Oh, I forgot an RL here. Wait, so V Thevenin. Oh, yeah, because we're supposed to multiply this whole thing. This was basically I, but we have to have an RL up here. I forgot that. You see what I forgot here? We have to have an RL up top here because that's this RL here. So V Thevenin squared RL over 2 times R Thevenin plus RL squared is the function of P as a function of RL. And so to maximize that, as you're familiar with from calculus, we're going to take dP dRL. And that's going to equal V Thevenin squared over 2 times what do you do? We're taking the derivative of that thing, so it's going to be the derivative. Wait, what is it? It's R Thevenin plus RL squared. It's like 1 times R Thevenin. I haven't done this kind of stuff in a long time. 1 Thevenin plus RL squared minus, oh yeah, it's the derivative of the top, right? The derivative of the numerator, RL, which is 1, times the bottom, and then it's the top times the derivative of the bottom. And is it actually minus? It's minus the top times the derivative of the bottom, which is 2 times, glad we're not doing a calculus competition tomorrow. Over the square of the denominator, R Thevenin plus RL to the 4th. And we set that equal to 0. And when we set that equal to 0, we can find that we're going to have essentially yeah, we can't really, if we're stuck with positive resistances, we can't really do much with the denominator, but the numerator is kind of interesting. Yeah, if we could set that numerator equal to 0, let's see, the numerator is going to be an R Thevenin plus RL again. Times, what's left is R Thevenin plus RL, and then a minus 2RL. And we set that equal to 0. And that's going to equal 0 when RL equals R Thevenin. Okay, so finally, so that means to get the maximum power to the load, I'm going to move to the next slide because I ran out of room here. Are you ready? Okay, you want to get the max power to the load. What we should do is essentially let Z load equal the complex conjugate of the Thevenin impedance. In other words, set RL equal to R Thevenin and XL equal to minus X Thevenin. And when that happens, the P max will equal V Thevenin squared over 8 R Thevenin. Okay, and that's because of this formula here, V Thevenin squared, you get 2 times R Thevenin plus RL squared in the bottom. Oh, and you got RL on top there. So, but RL is R Thevenin, so you have an RL over 2 R Thevenin squared, and it should work out to be 8 R Thevenin. But why is that? Because this is going to be 2 R Thevenin when RL equals R Thevenin. That's 4 R Thevenin squared, 8 R Thevenin. But then we got, oh yeah, then the RL just kind of takes away one of those R Thevenin. So yeah, it's 8 R Thevenin on the bottom. then the question is, suppose the load is only a resistor. What if you just have a light bulb? In that case, you cannot actually mess with the reactance anymore, but you can set the compromise is to set the load to the magnitude of the impedance. We didn't prove that, but that's the formula for that. So if you have the option of setting a load anything you like to get the maximum power to your load, you could choose the conjugate of the Thevenin impedance of the circuit as your load, and you can, in many cases, do just that. And there's a thing called load balancing, which is what factories can do to kind of optimize their power consumption and minimize their power bill to get the most power from the power that they're actually given from the power company. And so if they have the ability to adjust the reactance of their load, they can choose to get the most power. But then, of course, if you just have a resistor, you have to kind of stick with that. Now we're going to look at a couple questions here, and we'll do this tomorrow. Finding the load impedance that will receive the maximum power and what that maximum power is. And then if we just had a resistor, what would that resistor value be? And then we go into how we do the power factor correction. So that's what we'll be doing tomorrow. Any questions?
Go back to the complex power slide.
Complex power slide? Yep. That one? The next one? Mm-hmm. The S bar equals 128. That's 30 times 4.286 angle minus 13.24. Yeah, that's just the result of that. Okay. Catch you later. Mm-hmm. So the power factor, we're going to talk about that when we do load balancing. What the power factor represents is the percentage of the power that you're actually using. So it's a percentage. So you're given the. I'm glad you asked that. I should have said that. So the you're getting this apparent power from the power company, but what you're actually using, converting into usable actual work, essentially, is the average power. And the power factor is how efficient you are, essentially, the power you're given. Yeah, I should have mentioned that. That's an important concept. We're going to look at that more tomorrow, then. Yeah. You tell that it's leading because it's, where is that? It's leading because it's positive. It's a negative angle. Yeah, so with a negative, when the impedance angle is negative, that means it's leading. That's the situation where we have a capacitive load. And as we worked out in the lab yesterday, when we had a negative impedance angle, you actually got a positive angle for your current phase. Your theta I was greater than 0. And so that gave you a theta v minus theta I of negative. Yeah. Yeah, it ties together from that. Yeah, that lab is actually really useful to kind of get stuff. Yeah. Sure. Good. Mm-hmm. Yeah. Good. Yeah. Okay. Okay, cool.
So I'm not sure what to decide. I mean, my interest now is also I'm interested in this,
Yeah.
but you know, like really what is the difference? What is the engineering part of the major in computer science and engineering? So it's pretty much the same as
So UCLA calls theirs computer science and engineering?
yeah, so we have both like science by itself
Mm-hmm.
and when we just thinking like I'm assuming that major is the same electrical engineering.
No, I wouldn't say so because it doesn't say electrical in it.
Okay.
It sort of implies computer science and computer engineering. So you're going to get courses, and you could probably find out if you look at the program description and what courses you would take and compare those to Berkeley. You'll probably see they're quite a bit different. Computer engineering, yeah, computer engineering side of computer science, and you get a mix of both, right? And so, yeah, it's and there's probably some opportunities to to mess with that a little bit in terms of the electives. Requirements, I'll tell you. So here's the curriculum for the UCLA Computer Science and Engineering program. And so you start off with basics. This is computer architectures. You would have to take this double E. Physics, okay. Software. You do have to do logic design. Okay, of course that makes sense. Calculus, linear algebra. Okay. Electrodynamics. Well, okay. Well, no, that's physics.
More like a
operating systems, digital design. Because you're working with hardware, computer engineers are going to have to do digital design.
Yeah.
And then network fundamentals, which you probably won't get in an electrical engineering program. Circuit theory, done. Systems and signals, that's cool. Hardcore, that's core double E. Algorithms, circuit analysis 2. More computer science stuff. And a bunch of electives. And then, the electives are involving electrical and computer science, right? So like I said, you probably have some overlap in how you can sort of get pretty close to probably either one, but they're not exactly the same. Let's look at Berkeley. Core courses are similar. It doesn't tell you what these things are. It's annoying. So there's different areas that they
Yeah.
focus on. Okay. One course must provide a major design experience and be selected from the following list. So, so these are the areas. So
Yeah,
so you have a lot broader choice of emphasis, I guess. You could focus on quantum computing, but that's just one class. Um, like semiconductor devices, if you want to work on analog or digital, there's a lot more computer architecture signals. Robotics, do AI. Yeah, it's a little hard to figure out how this turns into an actual plan, but you can kind of see maybe it's a little broader than the UCLA one. But we didn't look at the electives there either. I think if you scope around, the Berkeley catalog, you could probably piece together what your choices really are. And if you have an idea of where you'd like to go at this point, you can probably get a sense of which one's going to be better suited for you. Berkeley? Okay. Good.
Or at the technical program,
Mm-hmm.
so I can ask how it's like what is the major focus, or if you can make up your own focus.
Mm-hmm.
That, or you focus more on computer science classes, and you have to take electrical classes, or the opposite. You focus more on the electric part, and you just have to take some of the computer science classes. But I don't know if how they arrange the classes.
Yeah. I mean, it sounds like you have quite a selection because, you can do a lot of CS type stuff or a lot of EE stuff. There's really a lot of opportunities there. So yeah, I don't know. Oh, there's a worksheet. Wait, admitted. So if you're admitted 2017 or later, then this might actually be a little helpful.
Okay.
So I guess for all requirements. Well, you still got to scope around and figure out what all these things, what to go in there, but
It seems like you have to choose from.
yeah. Well, while you're there, maybe you can arrange to see a counselor an advisor for the program.
Yes.
And if you actually, when you're going next week?
I think
This Friday. You might not have time, but if you put together like a sample plan of what you think you'd like to do, you could kind of run it by him and see, is this going to work there, or did I forget something? Yeah. I know, it's tough to decide. Oh, I hate those decisions.
yes. I'm glad that I got.
It's good. Those are really good schools. Yeah.
It was sad because the first letter that I received was from Canada. They rejected me. So I just thought, okay, I just seems like the ranking.
Yeah.
So I assumed that is it's like good time on the top with as well.
Yeah. Yeah.
Pretty much I applied to 6 species.
Wow. Okay. Did you go to Irvine? What other ones?
Irvine, Santa Cruz.
Yeah.
Ladies.
Okay. Okay.
Now in couple. My partner is thinking what to play. But then this thing happened.
Right at the time you were applying? Right at the time you were applying, huh?
Yeah. So was the time to this was the application. The
Yeah.
job, so
Yeah.
that is okay.
Yeah. I don't know. I mean, Berkeley's a great school. Yeah. You're gonna do some really awesome stuff there.
So that's why I'm okay. And then both are good schools, but honestly, like, which program to choose from.
Yeah.
We don't know where I'm from.
Yeah. Well, if you want to, after you do some research, run some stuff by me. I can give you my take on what you've chosen. But my major was kind of strict double E, but it was also a combined program at MIT, similar to Berkeley. Berkeley and MIT kind of they've structured their programs pretty similarly in terms of, they both call them electrical engineering and computer science. But when I was there, the tracks were, I think you either had a computer science track or a double E track. Now there's a computer engineering track at MIT too, because they didn't have that field at the time. But yeah, and my emphasis was sort of in communications engineering. So, but I don't know what I would do now if I was going back to school. There's so much cool stuff going on in machine learning, artificial intelligence.
Oh yeah, that's why.
Such a race right now. I was reading. China has this huge data set, so they've got this data advantage. I think it was the Financial Times was kind of was showing how the number of patents that are being applied for in these different technical areas, in terms of like big data and what's the other one besides? There's like the U.S. is still leading China in machine learning, but China has so much data, data science and big data stuff. China's leading the way. They were talking about they have a facial recognition system. I think it's recognition, just recognizing people from the face image, because they have 1.5 billion photos in all of their police files.
Oh yeah. Some areas of the city that are considered like risky, placing cameras to just, by watching the people walking by, they can tell who is the person. Yeah. Yeah, so probably, at the moment, focus is more into computer science, artificial intelligence is one of the things that I like to work on. And of course, electrical things are really interesting.
Yeah. Yeah.
And I know they have like plain computer science, but it's not as they give you freedom.
Sure.
To take language classes or art classes.
Electives.
More electives.
Yeah.
This one is more like just focus on technical stuff.
Yeah. Yeah, I don't know anyone else who's down there at UCLA at the moment. I think they had somebody go down there in mechanical engineering a couple of years back. He might, if you wanted to ask him just about what he liked about UCLA or not. And we have some folks at Berkeley, but again, I don't think they're in AA. I think they're in one. I think a couple are in chemical. We may still have somebody there in mechanical engineering.
And I tried so they invite us to on Facebook.